Hello, everyone. Welcome to today's webinar, which is brought to you by Bettersize Instruments in partnership with AZO Network and is titled Optimizing Additive Manufacturing with Particle Analysis. A big thank you to the team at Bettersize for making this event possible and to you in the audience for joining us from across the world. Before we get started, a couple of points about how to get the most out of your experience today. Firstly, the event is being recorded. We'll share the on-demand link with you within the next 24 hours. So if you enjoy what you see, or you've got a colleague or peer who might benefit from seeing the content as well, please do share with them that recording when you get that email. Refreshing your browser normally resolves any technical issues, but if this doesn't work, send us a message using the Q&A box. Our backend team will get you back up and running as soon as possible. There are several handouts available. You'll find them on the left-hand side of your screen. You can download those at any point today. Please do take a look at that before you leave the webinar today. So the webinar is going to consist of two presentations and an audience Q&A session. We're delighted to welcome first Dr. Beverly Barnum, Senior Application Scientist at Bettersize Instruments. Dr. Barnum received her Bachelor of Science degree in Chemistry from California State University and earned a PhD in Inorganic Chemistry from the University of Pennsylvania. Recognized for innovative problem solving, Dr. Barnum is a highly accomplished scientist committed to advancing technological solutions, and we'll be getting things started for us in just a moment before handing over to Viola Shen, Application Scientist at Bettersize Instruments. Viola is an application scientist at Bettersize, holding a master's degree in chemical engineering from the University of Southern California. She specializes in powder characterization and particle size analysis using advanced light scattering techniques. At Bettersize, Viola focuses on optimizing particle analysis methods, driving innovations in the advanced materials industry. Big welcome to you both today. As I've mentioned, there will be a Q&A following the presentations, so please send those in as and when they come to mind using the Q&A box, which you can find on the right-hand side of your screen. Any we don't have time for today, we'll ask the team to follow up via email at a later date. Okay, I'm now delighted to welcome Dr. Barnum to get things started. Dr. Barnum, over to you.
Thank you for that kind introduction. Hello, everyone. Today I'm going to talk to you about additive manufacturing, AM for short, and the importance of particle analysis in optimizing AM processes. Additive manufacturing opens up a world of possibilities by enabling the creation of exciting and complex components with unparalleled efficiency, sustainability, and cost savings. From aerospace and automotive to healthcare, consumer goods, and even prosthetics and beyond, AM offers greater design flexibility, faster production, and lower costs for smaller batch or highly customized products. The overview for today's webinar, we will explore how particle analysis is an essential tool for optimizing AM processes, ensuring high quality, consistency, and material efficiency. Here's a brief outline. I'll review the basics of additive manufacturing, the importance of particle characteristics, and lastly, how particle analysis enhances additive manufacturing. In part 2, my colleague Viola Shen will discuss several practical case studies and applications. So why focus on particle analysis? In additive manufacturing, the quality of manufactured components is highly dependent upon the properties of the raw materials, specifically the powder or particulate feedstocks. To achieve top quality, it is essential to use raw materials with optimal physical and mechanical properties. Particle size, shape, and distribution influence everything from flowability to sintering and efficiencies, ultimately affecting the precision, mechanical properties, and surface finish of the final product. What is additive manufacturing and why is it important? Additive manufacturing opens the world of design opportunities without the limitations of traditional subtractive manufacturing. Key characteristics of additive manufacturing are its layered construction. It's a process of creating objects by adding materials layer by layer based on a digital 3D model. Additive manufacturing builds objects by depositing material only where it's needed and creates these 3D objects by assembling successive layers of materials that are formed on top of each other. This allows for complex geometries and customization. There's a wide range of materials available, from metal, plastic, ceramics, even food products to human tissue. Additive manufacture is ideal for small batch production and quick prototyping, and accelerates the product development cycle by allowing rapid iterations. Prototypes can be created quickly and tested, shortening the time to market for new products. Additive manufacturing offers greater design freedom, allowing for intricate and customized designs tailored to specific requirements. This is particularly valuable in industries like healthcare, for example, to customize prosthetics or dental implants, and aerospace, where we need custom lightweight parts. Traditional manufacturing methods have limitations when it comes to producing complex shapes or internal structures. Additive manufacturing overcomes these limitations, enabling the creation of intricate designs like lattice structures or internal cavities that might be impossible or expensive with other techniques. Additive manufacturing minimizes material waste as it only uses the material necessary to create the object. This leads to cost savings and is more environmentally friendly. And there's reduced upfront costs as there's no need for custom molds or dies for small production runs or highly specialized components. Additive manufacturing can be more cost effective than traditional techniques. Compare this to these traditional manufacturing methods. I sort of view this as sandcastles versus ice sculptures. Traditional manufacturing involves subtractive processes where machines remove from a larger block to create the final product. These techniques include machining, injection molding, and forming, among other techniques. These methods are efficient for producing large quantities of identical parts, and this is ideal for mass production. And while it's able to use a wide range of materials, including metals and plastics and composites. However, there are high upfront costs due to the need for molds or dies and other specialized equipment. And at its heart, this generates significant material waste as the excess material is cut away from the starting block. So these are the key differences between traditional manufacturing and additive manufacturing in production volume. So the traditional methods excel in high volume production, while additive manufacturing is more suited for low volume and custom production. Additive manufacture allows for more complex and intricate designs compared to traditional methods. Additive manufacturing is more material efficient, whereas traditional methods generate much more waste. Additive manufacturing can be more cost effective for small batches due to these lower tooling costs, while traditional methods benefit from economies of scale when we scale to mass production. So both methods have their strengths and can be used complementarily to optimize manufacturing processes overall. When we talk about different forms of additive manufacturing, 3D printing is a form of additive manufacturing. However, additive manufacturing is a broader term that encompasses a wider range of processes. Electron beam manufacturing and selective laser melting are also considered additive manufacturing processes. Neither of them builds layers of material, but they still involve the creation of objects by adding material. It's worth mentioning that additive manufacturing is a more common phrase in industry and commercial applications, whereas 3D printing is more commonly used as commercial and recreational applications. Some key technologies used in additive manufacturing include FDM or FFF, which is fused filament fabrication. This is the most common type of 3D printing. It works by melting and extruding a thermoplastic filament layer by layer to create a part. FDM is popular for its simplicity and cost effectiveness. This is the most commonly known additive manufacturing process. Selective laser sintering is a method that's great for creating strong functional parts with complex geometries. Laser sintering creates durable components by use of a carbon dioxide laser to fuse together powdered materials, which are usually plastic, metal, or ceramic, into a solid structure. This type of additive manufacturing does not need support assemblies and can make incredibly complex parts. SLS is best for projects that require air or watertight construction. Stereolithography uses a precise UV laser to cure very thin layers of liquid resin into solid layers, forming a hardened plastic object. This type of additive manufacturing is often used in projects where a smooth finish is required. Direct metal laser sintering is similar to SLS. It specifically uses metals. A laser fuses or melts the powdered metal layer by layer to create solid metal parts. DMLS performs microwelds using this high-powered laser to form metal and alloys into the desired part. This is the toughest form of additive manufacturing and can be used to make strong and durable components. These are often used in aerospace and medical applications. Let's discuss briefly the materials used in additive manufacturing. Additive manufacturing uses a wide range of materials, including polymers, metals, composites, ceramics, and biomaterials. Different AM technologies have different material requirements, and the success of the process heavily depends on the properties of the starting material. Each of these starting materials is suited for different processes and applications. For polymers, these are commonly used in processes like FDM, SLA, and include materials like PLA, ABS, PEK, PEKK. So these are used in many applications, including aerospace, automotive, and biomedical. Metals are used in DMLS and SLM, and most common materials include aluminum, titanium, stainless steel, Inconel, and cobalt chrome. Combining different materials to enhance properties, we can use composites, and these can be created during the printing process or start as premixed materials. Common composites are carbon fiber reinforced polymers, glass fiber composites, nanocomposites, hybrid composites. All these are used to create parts with enhanced properties for various applications. Again, being used in aerospace, automotive, and medical industries. And ceramics are used for high temperature applications. And advanced ceramics manufacturing include materials such as alumina, zirconia, silicon carbide, silicon nitride. And these are used in applications from aerospace components to biomedical implants due to their unique properties and design freedom offered by using additive manufacturing. A number of resins are used in additive manufacturing, and these cater to a wide range of applications from prototyping and dental models to aerospace components and flexible parts. And finally, biomaterials. Again, the materials chosen there are chosen for their biocompatibility, biodegradability, and ability to support biological functions. And these are ideal for medical and tissue engineering applications. There are challenges in additive manufacturing despite their advantages. So you can have inconsistent part quality, the variability in the final properties related to strength, surface finishes of the produced parts can be affected due to inconsistencies in material characterizations. Material waste, while it's minimal, improperly characterized powders or particulates may lead to more defects and wasted material. In terms of powder aging and recycling, how reused powders in processes like SLS or DMLS lose their flowability would affect the production quality and layer resolution. Achieving fine detail and resolution depends on particle size and distribution. So understanding the particle characteristics, physical characteristics of these powdered materials are critical in determining how they behave in the additive manufacturing processes. Proper analysis of these particles can help mitigate risks like poor powder flow or incomplete sintering in your final product. So what are the key particle parameters to consider? Particle size distribution. What is that? Particle size distribution refers to the statistical distribution of particle sizes in a sample. It provides information about the range of particle size present, the ratio of particles within each size range, and the distribution pattern of particle sizes across the sample. The size of the powder particles affects the flowability and the packing density of the material. A narrow PSD, particle size distribution, may improve uniformity and layer deposition, while a broad PSD can enhance packing density for certain applications. Particle shape. The shape affects both the flowability and the behavior during sintering or melting. Spherical particles typically flow better and pack more efficiently compared to irregular or angular particles. In terms of surface area, This affects the powder's reactivity, thermal behavior during the additive manufacturing process. Higher surface area powders may react more readily during sintering or bonding, but they can also lead to issues like oxidation in metal powders. There's a whole range of densities that we need to discuss. Skeletal density and true density are related to the surface and interior structures of porous particles. Skeletal density is the ratio of the mass of the porous particles to the volume of the particles that exclude the open pores. True density, or also defined as absolute density, has open and closed pores that are not considered in the calculation of the volume of the porous particle. If there are no closed or sealed pores, skeletal density would be equal to true density. Now let's move on to bulk density. The ratio of a powder's sample mass to its volume is a bulk density. Bulk density takes into account the powder's arrangement, density, and how it's prepared, stored, or treated. The tap density is the ratio of the powder's mass to its volume after mechanically tapping it in a cylinder until it reaches a constant volume. So tap density is increased in the bulk density of the powder after tapping. So bulk and tap densities of powders determine how well they can be packed during the additive manufacturing processes. And the porosity of a powder is the ratio of the volume of voids in the powder in its bulk volume. And the porosity of the powder may result in internal defects in the final part in additive manufacturing. So why do these characteristics matter? I kind of mentioned a few things here. So analyzing bulk and tap density can help you understand how compressible and flowable a powder is. And these properties are important for storing and transporting powder and bulk samples. In terms of flowability, consistent flow is essential for reliable deposition in powder-based processes such as SLS or DMLS. Layer thickness and resolution. Smaller particles allow for thinner layers and finer resolution, but may lead to issues with powder handling and flow. In terms of mechanical properties, these particle characteristics directly influence the final part's mechanical properties, such as tensile strength, hardness, and fatigue resistance. Balancing these properties affects the final product. Tensile strength is the material's ability to withstand stress before deforming or breaking. It's an important characteristic for evaluating a material's strength. Process-specific defects such as surface roughness and weak interlayer adhesion can lead to premature failure. Hardness is the material's ability to resist deformation, wear, and external forces. It's affected by a number of factors, including microstructures, cooling rate, alloy composition, and heat treatment. And fatigue resistance is the property of a material that allows it to resist breaking down over time under the influence of changing workloads. Additive manufacturing parts are typically less resistant to fatigue than conventionally fabricated parts, but they can be overcome. Additive manufacturing parts can have defects like lack of fusion, gas pores, surface roughness, and game boundaries that can make them less resistant to fatigue. And the material microstructures, including its grain size and phase distribution, affect the fatigue resistance. Smaller grains can better absorb and dissipate energy from loading, while certain phases can reduce crack propagation. The role of particle analysis in feedstock optimization. Particle analysis can help optimize the feedstocks used in additive manufacturing by ensuring that the powders meet specific criteria for size, shape, and flow. By precisely characterizing powders, manufacturers can select the right material and adjust the process to achieve better additive manufacturing quality and consistency. What are the particle analysis techniques? Common ones are laser diffraction, dynamic light scattering, SEM, X-ray diffraction. Diving into these really quickly, laser diffraction is a widely used method for measuring particle size distribution and is particularly useful where narrow PSD is critical. This typically measures diffraction in the particle size range from 40 nanometers to 3.5 microns. 3,500 microns. The advantage is that it's fast, non-destructive, and suitable for a wide range of particle sizes. But cons are math involved for laser diffraction assumes that the particles are spherical. Dynamic light scattering is often used for smaller particle ranges in the nanoscale. This ensures the consistency of the microstructure of the formed parts. Particle size range here is less than a nanometer to about 15 microns. And the pros are this provides hydrodynamic size and is good for small particles and colloids. Again, the cons are that the math assumes particles to be spherical and that this process is also affected by sample preparation. Scanning electron microscopy is used to analyze particle shape and morphology, especially for metal powders where sphericity is essential for optimal performance in additive manufacturing. Pros are that this has high resolution and gives detailed surface morphology. The cons are this is an expensive and long process and is destructive, requiring conductive coating for non-conductive samples. XRD, or X-ray powder diffraction, is used to study crystal structures and phase identification, which is crucial in metal and ceramic additive manufacturing processes. The pros are this determines the crystal structure and phase identification. The cons are it requires a crystal structure, and so you have to have crystalline samples, and there's a complex data interpretation involved in XRD. By understanding the relationship between particle properties and additive manufacturing parameters, manufacturers can fine-tune parameters like laser power, layer thickness, and scanning speed to achieve better results. And this leads to fewer defects, improved mechanical properties, and enhanced surface finishes. Data on the particles, specifically their size, their shape, distribution, is crucial for optimizing additive manufacturing processes because it directly impacts the flowability, packing behavior, and ultimately the quality of the final part, allowing manufacturers to fine-tune powder feedstock properties to achieve desired outcomes like improved density, surface finish, and mechanical strength. Key points about particle data help optimize additive manufacturing. By analyzing particle size distribution, we can ensure a consistent powder bed. And this is critical for achieving uniform layer deposition during the AM process. By understanding particle size and shape, manufacturers can optimize the powder flow and spreadability within the machine, ensuring even powder distribution across the build platform. Particle size and surface chemistry affect how particles melt and fuse together during the additive process. So these melt characteristics impact the final part's strength and density. Particle size and shape directly influence the surface texture of the final part, with smaller and more uniform particles generally leading to smoother surfaces. And by analyzing particle size distribution, manufacturers can minimize waste by optimizing powder usage and reducing the need for excess material. By choosing the right powder with the optimal particle size and shape for the desired application, we consider factors like strength, density, and surface finish of the final product. By adjusting the processing parameters like the laser power and the scan speed based on the particle characters that are known, you can achieve optimal melting and fusion during the process. And by regularly monitoring particle size distribution to identify potential issues in the powder feedstock, this allows quality control to maintain consistent quality. So to quickly review, we've discussed the basics of additive manufacturing, and in reviewing the technology, we've seen the materials used and the challenges, and this can lead us to understand the importance of particle characterizations like PSD, shape, surface area, density, and other characteristics. Now we understand that it's important to know the raw materials in order to optimize the additive manufacturing process. We can see that analyzing our particulate raw materials is the key to success. And now we'll move on to part two, my colleague, Viola Shen, application scientist at Bettersize Instruments, on more details on how to perform these characterizations.
Thank you, Dr. Barnum, for your comprehensive introduction. And hello, everyone. I'm Viola Shen, application scientist of Bettersize Instruments. Now let's see how we approach particle analysis and powder characteristics to assess the performance of additive manufacturing materials. There are three main topics in my sharing, including dynamic image analysis combined with laser diffraction, powder characterization techniques, and true density analysis. We will explore these topics from several perspectives: how the measurements are performed, what Bettersize offer, and some real application examples. So let's start with the principle behind laser diffraction technology, which can be used to find out the particle size of the additive manufacturing materials. As the figure depicted on the left, when light shines on a particle, light scattering occurs as a combination of four phenomena: reflection, attenuation, refraction, and diffraction. The diffracted light projects a pattern on the screen, forming a series of concentric circles of varying intensity, known as the array pattern. With a fixed wavelength and distance, these patterns change systematically with particle size, as the figure in the middle showing large particles and small particles. In practice, particles of different sizes produce a combined diffraction pattern or spectrum, allowing comprehensive particle size distribution analysis. This makes laser diffraction an essential tool across diverse applications. So, what instrument can Bettersize provide the laser diffraction technology and particle size analysis? The answer is the Bettersizer 2600. The figure on the left side is our patent optic structures of the laser diffraction particle analyzer. The process begins with sample addition and dispersion to achieve even particle distribution. Then the system collects the scattering spectrum, which is analyzed to produce a particle size distribution result, detailing particle content across specific size ranges. Key advantages of the Bettersize 2600 include our patented optics, wide measurement range, rapid testing with high accuracy, and modular design suitable for water-based, solvent-based, and even dry samples. Moreover, the latest module of the Bettersize 2600 has recently debuted, offering enhanced capabilities that extend beyond just particle size distribution results. Yes, that is particle shape analysis. Owing to its modular design, the Bettersize 2600 effortlessly integrates a dynamic image analysis system, PIC1, which extends the measurement range up to 3,500 microns and providing quantitative particle shape analysis in real time. From the figure on the right side, as we can see that the PIC1 features a dual camera dynamic image system. As the dispersion system transports particles through the sample cell, the high-speed camera capture and convert images to digital format for real-time analysis. Enhanced with PIC1, Bettersize 2600 can now provide particle size distribution and shape analysis simultaneously. And thanks for Dr. Barnum has already mentioned the importance of particle size and shape in additive manufacturing. So next we will use a real example to find out the powerful combination of these two advanced technologies. Optimizing particle size and shape is crucial for improving the efficiency and quality of powder bed fusion. Therefore, in this case, the Bettersize 2600 was used to analyze these parameters of 4 powder bed metallic samples. The results are showing both the particle size distribution graph and the table 1 on the right. We can see that the D10, D50, D90, and span values for sample 1 to 4 are listed in the table. According to these important values, sample 1 has the largest particle size while sample 4 has the smallest, suggesting finer particles. The span value shows the sample 2 has a narrow distribution compared to the other samples, indicating more uniform particle size distribution. So can we Simply say the sample 2 is the best? Let's dig deeper with pick 1, the image analysis module. With the combination of pick 1, more than 20,000 particles from these 4 metallic powder samples were measured in time. The figure 2 on the left side presents images of individual particles from 4 test powders captured during the shape evaluation. Table 2 provides the circularity of all samples, calculated by the Bettersize software. So circularity values indicate how closely particle resembles a sphere, with value of 1 representing a perfect circle. As we can see, sample 2 has the highest circularity value, suggesting more spherical particles and uniform results, which highly align with the particle size measurements. So with this example, we can see that the Bettersize 2600 is capable of combining laser diffraction and dynamic image analysis to deliver precise size and shape analysis for the optimization of powder bed fusion process. And in Dr. Barnum's discussion, she also emphasizes the importance of evaluating the additive manufacturing materials by measuring critical parameters such as angle of repose, tap density, flowability. While it is true that many instruments can measure these parameters individually, is there a single device capable of measuring all these powder properties efficiently, thereby offering a more comprehensive analysis? Mm, Yes, there is one, which is the Powder Pro A1, provided by Bettersize. It is a high-performance instrument capable of measuring and analyzing 14 different powder characteristics, including like tap density, compressibility, flowability, and the rest are listed in the right side. It incorporates advanced technologies such as Wi-Fi enabling intelligent control, image processing, 3D electromagnetic vibration, and rotating tap density measurement. Let's dive into the details. The Powder Pro A1 provides a highly compact and efficient solution with several notable advantages. This instrument is equipped with a high-definition charge coupled device, the CCD camera, that captures clear images of the powder pile. This allows for the precise measurement of critical flowability parameters such as angle of repose, angle of spatula. And thanks to the advanced image processing technology, these measurements are not only accurate but also highly repeatable. The Powder Pro A1 also includes an integrated sieving feature allowing for sieve analysis, which is very important for determining particle size distribution. This functionality is invaluable for assessing key powder properties such as flowability and compressibility, as it provides a comprehensive understanding of how particle size affects material behavior during processing and end-use application. Next, we will use another application case to depict the capabilities of the Powder Pro A1 with these advanced functions. In selective laser sintering (SLS), consistent powder flow is essential for uniform layer deposition and defect prevention in printed parts. So this application case demonstrates how the Powder Pro A1 was used to evaluate various parameters, including the angle of repose, angle of spatula, tap density, bulk density, compressibility, and uniformity. Each test value from the Powder Pro A1 corresponds to an index based on the car index method within the software, allowing for a direct flowability evaluation. This result indicates that alloy 3 sample shows the best flowability, making it ideal for the SLS technology, while alloy 2 shows poor flowability and may require vibration to enhance flow and prevent bridging. This analysis provides important insight into the behavior of these metallic powders during processing, helping to optimize material performance and ensure uniform powder spreading for high-quality additive manufacturing builds. We've discussed the powder behavior of bulk powders, so now let's shift to another key aspect, true density. In additive manufacturing, true density impacts interlayer adhesion, material uniformity, and the mechanical properties of the final parts. So I'm going to introduce a reliable technique for true density testing, which is the gas pyknometer. Before I get to know what a gas pyknometer is, we need to understand the principle behind, which is the Boyle's law. It states that for a given mass at constant temperature, the gas pressure times the volume is constant K. By applying this law, a gas pyknometer can accurately calculate a sample's volume, which, when combined with the sample's mass, allows for determining its true density. Therefore, we can say true density is defined as the mass of a material divided by its volume, excluding any pores. A typical gas pyknometer is shown in the figure below. It has a sample chamber, a reference chamber, a pressure transducer, and 3 main valves: the fill valve, expansion valve, and the vent valve, which are used to control the gas flow. So imagine we are now using a gas pyknometer. We start the measurement by opening the lid and placing the sample in the sample chamber. And then we close the lid, keeping the expansion valve closed. And we open the fill valve to allow a specific amount of gas to enter the sample chamber, then close the fill valve. The pressure at this point is recorded as P1, and we have a formula here. Next, we open the expansion valve, allowing the gas to flow from the sample chamber to the reference chamber. And once the equilibrium is reached, the pressure is measured as P2, and we have another formula. Using Boyle's law and the known volumes of the sample chambers and the reference chambers, along with the recorded values of P1 and P2, the volume of the sample can be calculated by the software, with the sample's mass easily obtained by precise balance. We can then determine the true density. Compared to the traditional liquid displacement methods, the gas displacement technique offers several advantages. It is non-invasive, faster, and suitable for a wider range of materials, including porous or delicate samples. With the gas pyknometer from Bettersize, we benefit from a lot of enhanced capabilities. The Betterpick, combined with its EasyPick software, can provide extensive measurement options, including volume, density, open cell content, and solid content. It offers rapid and highly accurate measurements with accuracy of 0.02%. And operates within a flexible temperature range from 10 to 65 Celsius degrees. The system can also be equipped with 316 stainless steel sample cups, ideal for handling corrosive materials such as cement to ensure long-term durability. With a volume capacity ranging from 1 to 100 cc and automatic chamber volume matching, it adapts seamlessly to various sample sizes. In summary, the Betterpick 3.0 effectively measures hard forms, liquids, solids, semi-solid mixtures, and slurries, making it a highly adaptive solution across industries. This application case demonstrates true density analysis for various powder feedstock and 3D printed parts using the Betterpick 3.0 gas pyknometer. It provides precise insights into the powder purity and essential metal properties, such as direct strength and hardness. The table shows consistent true density values for each sample with minimal standard deviation, underscoring the accuracy of our gas pyknometer. And this High precision measurements are vital for evaluating the uniformity of material properties, ensuring that powders and printed parts meet the stringent standards of industries like aerospace and medical manufacturing. By adhering to ASTM, ISO, and USP standards, the BERPIC 3.0 assures that results align with the additive manufacturing industry demands for reproducible results. In summary, Bettersize offers an extensive suite for particle size and powder characterization solutions designed to address diverse industry needs, with a strong focus on additive manufacturing. Combining dynamic image analysis and laser diffraction, the Bettersizer 2600 and PIC1 provide precise particle size distribution and shape analysis, essential for optimizing powder behavior in the powder bed fusion process. The Powder Pro A1, a powder characteristic tester, serves as an integrated solution for assessing powder flowability, which is a key factor in achieving consistent layer deposition in 3D printing. Also, the Betterpic 3.0 gas picnometer utilizes the gas displacement methods can ensure reliable true density measurements and supports the correlation between powder and final part density. With all these advanced tools, Bettersize empowers additive manufacturing industries to achieve greater accuracy and efficiency in material analysis and quality control. That's all for my today's sharing. Thank you, everyone.
All right, fantastic. Thank you very much, Viola. Thank you very much, Dr. Barnum. We're now going to start the Q&A part of the webinar. We'll just bring Viola back as well. Just before we do, though, we have a couple of offers to share with the audience. So appearing on your screen just now will be an offer to do with a free sample. And Beverly, perhaps if you could just briefly explain what that one's about.
Thank you, Danny. If you send samples for testing to our labs in the United States or Canada, our US team, which includes me, we can handle the analysis of these samples. And from other regions around the world, we have local experts that can provide detailed reports. And then all you would need to do is basically submit proper form, and then we can get started on analyzing your samples.
So I'll come to you for the first question, Beverly. It's asking, how does particle surface roughness influence powder fusion rates?
Okay. So as I mentioned earlier, particle surface is important in AM. So what happens is that rougher particles can increase the friction and reduce the flowability. And this can lead to, within the machine itself, the mechanism itself. And during the process, this friction and reduction of flowability impacts the packing density, and this can lead to incomplete fusion during the manufacturing process. So if we have smoother particles, these tend to flow better, and these will fuse more uniformly.
Beverly, I'll come back to you for a second question. How does particle surface chemistry affect the binding and sintering processes?
Again, so the surface chemistry of particles influences their reactivity and interaction with binding agents. So if we have proper surface treatment, this can enhance the binding treatment and improve the sintering process when we bring in the energy. And this can result in a stronger and more cohesive art.
So, Viola, I want to bring you in on this one. How about this? How does PIC1 prevent resolution loss or image blurring when capturing high-speed particles?
Okay, so for this one, we anticipated potential issues related to the resolution loss or blurry images when tracking the fast-moving particles during the R&D phase. To address this challenge, we implemented a comprehensive solutions. Our system is equipped with high-speed cameras capable of capturing 120 frames per second, which allows for capturing rapid movements with greater clarity. Also, we pair the cameras with LED light sources that synchronize with the frame rate, minimizing motion blur and ensuring sharp, clear images. Moreover, the software includes a low exposure time setting, which helps to further reduce the risk of blurred images by reducing the potential for overexposure or motion distortion. So this combination of high-speed imaging, synchronized lighting, and optimized exposure settings guarantees that particle motion is captured accurately by Bearsizer 2600 with Peak 1, ensuring high-resolution imaging even in dynamic scenarios.
Here's another one for you, Viola. Do your laser particle size analyzer and Powder Pro A1 comply with 21 CFR Part 11 for testing 3D printed drug materials?
Yes. Both the Bearsizer 2600 and Powder Pro A1 fully comply with 21 CFR Part 11 requirements. So this instrument ensure compliance by implementing key features such as user access control, which restricts device operation and data modification to authorized personnel only. They also include an audit trail that captures all actions related to data creation, modification, and deletion for traceability. And additionally, the instruments guarantee the security of electronic records from unauthorized access. They also support electronic signatures to ensure that each signature is legally binding and cannot be repudiated.
Superb. And one more, Viola. Can the BetterPick 380 measure the open cell content of a finished hard foam produced using additive manufacturing? And if so, how does it work?
Yes, the Betterpick 380 can measure the open cell content of a finished hard form following the standard ASTM standard D6226, which is the standard test method for determining open cell content in rigid cellular plastics. So according to this standard, hard form samples must have 1 inch per side. To meet this requirement, Betterpick 380 provides foam cutting accessories for user convenience. And using the gas displacement method, the Betterpick 380 can accurately measure the true volume of the foam by excluding any pore spaces in the samples. And the open cell content is then calculated by comparing this true volume to the bulk volume, distinguish between the open and closed pores in the samples. So this approach can definitely provide high accuracy in assessing both the bone metrics and internal structure.
Okay, let's take this next one. What are some examples where optimizing particle characteristics led to significant improvements in final product quality?
So, let's see. So, in aerospace and medical applications, the optimization of particle size and shape has led to significant improvements in the mechanical properties, which are and the surface finish of parts. So, obviously, when we're dealing with aerospace and mechanical properties, we can't have roughness. We can't, and we also need incredible strength. Can't just drop in and repair those parts. So, by choosing the right particle distribution, we can enhance the fatigue life of critical components, which is a key requirement in aerospace and in medical applications.
Superb. What about, let's take this one here. Does microwave processing of materials fit into AM technologies?
Yes, actually, this is kind of an exciting new horizon in AM. So, microwave processing does fit in additive manufacturing, and one of the biggest examples is from Lawrence Livermore Labs, and this is microwave volumetric additive manufacturing. And unlike light-based additive manufacturing, microwaves can penetrate the opaque materials, and so this allows for a greater range of interactions in terms of using different feedstocks. Because we can have filled resins, ceramics, and composites that may not be compatible with current AM technologies. And also, so that adds into the material versatility that can be applied in AM. There's also a lot of heating because microwave energy can heat materials volumetrically, not just on the surface. So we can go to faster processing times as opposed to the normal convection heating methods that are used. And so this can be used to create complex structures, including metals, ceramics, polymers, composites, with a potential applications in electronics, medical devices, and again, aerospace, which is the current high demand areas.
Okay, Beverly, let's take one more here. What are the challenges in maintaining consistent particle quality throughout the manufacturing process?
So some of the challenges in maintaining consistent particles quality is in order to, let me try that again. So in order to maintain consistent particle quality through the process, we need to achieve uniform particle size and shape. We need to avoid contamination, and we need to ensure something that we don't always consider is stable storage conditions to avoid agglomeration or degradation of the powder. It can be great when we get it, but when we receive it, but after storing in non-optimal conditions, which generally are heat or humidity, we can get agglomeration or degradation of the powders. And so these are some of the issues that QC of the particles by using some of our instruments is key in avoiding.
Beverly, I think that's all I can see for yourself. Do you have any final comments before we wrap things up?
No, I wanted to thank everyone for their participation and thank you for joining us today. Again, we have, you can request a quote. We offer free sample testing. A lot of people may not be aware of Bettersize Instruments and Bettersize Inc., which is a U.S. arm of Bettersize Instruments. But Bettersize Instruments is proud to have their 30th anniversary next year in China, and Bettersize Inc. in the United States. We're growing, and we have multiple offices in the U.S. So remember to think about us when you need particle size analysis.
Superb. There's a lot of nice comments coming in as well, so that's great to see. Do you want to just take this one final question before we finish up? It's asking, do you have any advice which medium could we use to measure nickel alloy with the Bettersizer?
Yeah, so some of the instruments that we have, we've been using our S3 Plus and our 2600. We've been testing nickel alloy particles, and we just actually use water. And one of the key features of both of these instruments, which are based on laser diffraction, is that we have adjustable mechanical stirrers combined with built-in ultrasound that also has adjustable power levels. So we are able to optimize the suspension of these heavier nickel alloy particles while avoiding bubble formation. And this leads us to get reliable results. So this is a common application that we've used, and either these instruments, the S3 Plus or the 2600, have handled these without issues. And we just use, again, purified water for these devices.
Superb stuff. Dr. Barnum, thank you very much for sharing your expertise and time with everyone today. Thank you to everyone in the audience for joining us from across the world. I'll leave the webinar room open for a couple of moments. So if you hadn't had a chance to download those handouts or to click any of the links, you can do in the next couple of minutes or so. A survey will then appear on your screen. So if you could share your feedback with us, that would be wonderful as well. Dr. Barnum, thank you very much. And we wish everyone in the audience a pleasant rest of the day, and hopefully see you all again very soon.